Measures of central tendency provide a summary statistic on the center of a given distribution. This is also known as the average value of the distribution. The most common measure of central tendency, synonymous with that term average, is the mean, which is often symbolized with the Greek lowercase letter mu. And so we use mu when we're talking about the population mean. So if we had a room full of people, and that was the population that we were interested in, then we could measure the height of every single person in the room and say that is definitively the average height of the people in the room, the mean height of the people in the room. But typically, we can't actually get a measurement from every single person in the population of interest or every single item in the population of interest. So we typically work with a sample mean, which we symbolize with x and a bar over the top. So if x is the height of people in the United States, then the sample, the average height of all the people in the US, we could symbolize with x bar. And the calculation, this might be obvious to you, but the calculation of the mean, this what we typically call the average of the sample, is simply the sum over all of the items that we have. So if we have 1,000 people in our sample, n is equal to 1,000, and each individual height in that sample is xi, and so we sum over all of those individual heights up until our 1,000th person, and then we divide by however many we have. In this example of this sample of US heights, then we have 1,000 in that sample. So all we're doing here is we're summing up all of the individual data points, say all of the individual heights, and then averaging by however many heights we have. All right, so continuing on our discussion of measures of central tendency and the mean with a hands-on code demo, we're back in our Subject 5 Probability Jupyter Notebook, and you can use the table of contents to find your way to the section on the mean. And if it's been a while since you've executed any code in this notebook, then you might need to go up to runtime and run all the cells before. And yes, I am good to go here. So we just talked about this, so I don't need to go over that again. But let's talk about this quickly, which is that the expected value, which is what we were talking about in the preceding videos, we calculated the expected value of 5 coin flips, and we determined that that was equal to 2.5. So that expected value is equal to the long-term mean, the true mu population. So expected value is equal to the population mean. Let's use this hands-on code demo here to calculate how close a sample mean, x bar, is to the expected value. So we know that if we had an infinite number of samples, if we were able to get a very, very, very large number of items of, say, 5 coin flip experiments, then that will start to converge according to the law of large numbers on mu, the true population mean, and that would be equal to the expected value. But yeah, let's run an experiment with a smaller sample mean and see how close we get to the expected value. All right, so let's continue to use this heads count variable, which we created earlier on in this notebook. So this heads count variable we created up here when we ran 1,000 coin flip experiments with a fair coin, and each one of those experiments had 5 coin flips in it. So we're going to reuse that same variable here. And so yes, we have 1,000 5 coin flip experiments. That's our sample. And we can have a look at what those data look like. So you can see here on the first of the 1,000 coin flip experiments, we had 2 heads. And the same thing on the second and the third experiment. But on the fourth experiment, we had 3 heads. And so these are the first 20 5 coin flip experiments which we captured in this distribution here for all 1,000 of them. So, of course, we saw 2 and 3 heads were the most common outcome. And and we calculated in a preceding video that the expected value of this coin flip experiment is 2.5. So we already know what the expected value is, and we know that that's equal to the population mean mu. So 2.5 is what we're looking for. So do we get that over our 1,000 5-coin flip experiments? Well, in order to calculate whether we get that with our sample, we simply sum up over all of the samples and divide by however many samples we have. So that's what we do here. We sum up all of our samples and we divide by however many samples we have, which in this case is 1,000. And that gives us 2.47, which, yes, is indeed very close to 2.5, the expected value, which is the true population mean. So if you were to increase your sample size to 10,000 or 100,000 or a million, according to the law of large numbers, that sample mean would get closer and closer and closer to the true expected value, to the population mean. You can try that on your own time. Now, I kind of manually calculated the mean here just to show you how the standard mean calculation breaks down. However, because it is such a common operation, unsurprisingly, many Python numerical libraries come with a built-in function, and so of course NumPy does. So we can just use the NumPy mean method and pass in our variable that we'd like to calculate the mean of, heads count in this case, and of course we get the same value as when we did it in this slightly more manual way. Nice. So the mean, that's the first measure of central tendency that we're going to talk about. Up next, we're talking about another one called the median.